I can't hear anything. Why can't I hear anything?
Hello.
Oh, there you go. Cool. Okay. Is it just wait? There's more. No, it can't be this. Every system, nothing works. Why is it not? Oh, my computer's frozen. How many people are here? Because I can see 3 people, but I'm assuming there's more than 3 people. Like my windows are stuck. Do we have
I think we have 38.
38? All right. Well, that's not a bad number. So, okay. So I apologize for not being able to contact you about the exam, but actually I was just only today able to get access to Blackboard, like around 11 o'clock today. So something happened to my account. It was excessively disabled or something like that. I don't know. So, okay. So here's my take on all this excitement, right? So I know you all. I mean, I guess I could argue that like this doesn't really affect anything going on in this class, but I know you have a lot of other things going on and trying to figure it out with the other classes just takes time. So I'm going to at least temporarily put a hold on. I'm going to bump everything out a week. Okay, you know, homeworks and the exam. I won't add more material onto the exam. So the exam, but that will compress stuff later on a little bit. Do you know what I mean? Right. In the sense that we should keep moving forward with the material, right? But I get it. Homework is, you know what I mean, right? Even though we're not doing it through Blackboard, but I mean, I think, I know you had enough other stuff going on. So I will do that. Okay. So I guess that, so what I'm saying is the exam actually is going to get bumped out a week, assuming that the university can figure its business out by then. Okay. Does that make sense? And I will do the same. I know there's a homework due today. We'll bump that out as well. Okay. Now, as far as how do we communicate through class? So I think you should all know, right? Your email accounts work. Student email accounts work, but you cannot access them through the university webmail portal or whatever you want to call it. You know what I mean? Right? I don't know how many of you know this, but if you go to outlook.com or office.com, right? You and log in with your student, your UTEP identification, you should be able to access your UTEP email, your minors.utep.edu email through that. Okay. I'm just curious. Can you, I really want to know. So how many people knew that? Who did everybody, does everybody know that? Should I do a poll? I hear no response. Okay. We're going to do a poll. So if you, turn off your microphone. So I need to discuss, you know what I mean? Right. I'm going to, today I'm not instructor of the class. I'm department chair. Okay. So I want to know what's the situation, right? I need your help. That's what I'm saying, right? So how many people knew how to access their email?
Well, in my case, I gain access because I access through the Microsoft options. So I sign with my credentials in the Outlook webpage.
Okay, through Outlook webpage, right? Yes, yeah. So there's 3 ways to do it, really. You can either go through Outlook.com or Office.com, which I think basically route through Microsoft. Or if you had downloaded like actually Outlook, the application, onto your computer and you use that works as well. But obviously you can't go through the UTEP webmail. And I guess students use webmail, but I mean, webmail is terrible. How many people use webmail? Anybody? No? It's okay if you do. I'm not trying to shame you for using it. You know what I mean? Right? But it's not a great interface. It's kind of awkward. You know what I mean? Right?
I don't even know what webmail is, Professor.
Oh, you know, oh, so if you go to myutep.edu, one of the icons there is like webmail. And you can actually see your Microsoft email managed from Microsoft, but it goes through the university somehow. And so if you went through that way, obviously that's down because the university stuff is down. You know what I mean, right? Okay, so everybody can get there. So did you receive my email today? Okay, good. Okay.
Yes, I did.
Feel free to reply to that email. That's fine. You know what I mean? Like that, I mean, it's okay. Don't be offended, but that's like a burner email. I'm gonna like get rid of that once all this is over with. You know what I mean, right? So you can, Okay, the other one. What's the situation with your other classes? Are you having any issues with regard to communicating, or maybe some instructors being a little less than reasonable on some of those things?
I
Uh,
haven't. Oh,
Oh, I was going to say just that for my history class this semester, we had a quiz due on Sunday, which I fortunately had time to complete it because Blackboard got running again just in time for me to do the
Oh,
quiz.
really?
But even before and after that, after the quiz, the professor didn't address the whole system being down, so we didn't hear anything about an extension on that quiz or anything like that.
Well, now, so faculty, our email is handled by the university. So it's an Exchange server on campus, like in the union. So I don't have email. Nobody has email. No faculty have email, faculty and staff. So I hope they fix that because, like, I never really liked having my email. I'd rather have Microsoft handle my email, to be honest with you. So yeah, that's going to be the thing. So you will not be able to email faculty. I believe if you do try to email them, it's going to get bounced back. But now I believe everybody is on Blackboard, but Blackboard's like a crappy system to try and communicate on. You know what I mean, right? It doesn't really work. Microsoft Teams does work, okay? Because again, that is supported by Microsoft directly. So amazingly, even when I was on campus Friday, I couldn't access anything, but I could do MS Teams meetings. Okay, so you can definitely get in touch with faculty on that. Everybody's ID on Microsoft Teams is their email address. So mine is JF Chessa, whatever your email address is, whatever faculty it is, you can find them on Teams. Most mechanical engineering professors use Microsoft Teams. I don't know what people in history do. You know what I mean, right? They probably still use Post-it notes or something. I don't know what they do. Okay. But if you're having any issues in particular with classes, feel free to contact me, as the chair of the department, right? Okay. If you have friends that you somehow talk to in other classes, they can do the same. Obviously, if they're mechanical engineering classes, I can probably have a pretty significant, ability to address the situation. But even if you're having issues with other courses, at least try to let me know. It's a little more. I don't know exactly what I can do, but I can always try to contact those individuals and just say, it could just be a communication thing and they just didn't realize. Okay. Because nobody knew anything until, even the dean of engineering didn't. The first communication she heard was Sunday night, which was basically the same thing that they posted on Facebook, was that Blackboard is going to be on Monday. Okay. All right. So everyone else it's pretty reasonable. You're functioning. Yeah. I think you guys are going to be impacted less than anybody else. Another one, I think everybody should, you know, just as a word of advice, the university has not really disclosed what information was compromised. Do you know what I mean? Right? You all have social security numbers. The university has all your social security numbers, right?
Mhm.
I strongly encourage you to change passwords. Watch it. Do you know what I mean? Right? Maybe contact your bank. Make sure you know what I mean, right? Because I don't think anybody knows what's been accessed, right, or what way it is, or what they're trying to do. Just
Sure.
as advice. Yeah,
Was it a hacking or what was it?
yeah. It was hacked. It was hacked. Yeah. It was
Mhm.
hacked. Yeah. I don't know. Well, I didn't know who it was. I've heard everything from it was China. It was,
So they're still investigating what the
MSU.
situation is.
Yeah, no, nobody's saying, so I don't know what it is. Even talking to some people that are relatively high up the food chain, they still don't really know. You know what I mean, right? So the university is being, for better or worse, a bit closed-lipped on the whole situation. But I think that's all the more reason that you want to just make sure your own personal. I mean, it's a good thing to do in general anyway. Do you know what I mean, right? Because our information is just a function of society, right? It's all over the face of the earth anyway, right? Like actually, I mean, I don't know, like before this happened, I think Chrome was like, you have 6,000 passwords that have been compromised. You guys, your passwords, right? So I've been in the process of changing passwords, but it's probably not a bad idea that you kind of do that stuff anyway. You know what I mean? At least on the important things, right? I mean, I try to keep. I have, and you can't. So I have like stupid passwords that are very insecure, but they're for stupid things that have no consequence, right? Like my password for UTEP, because it's the password that controls like departmental accounts and research accounts, is ridiculous. I can't remember it, right? And I try to keep ones like that. And the ones that are important, you should change. You know what I mean? Don't use this, obviously everyone knows don't use the same password for everything, but you can use stupid passwords for stupid accounts, but on the important ones, you want to make sure you kind of change that stuff and make it, something you can somehow remember, but it's not easily hacked, So, all right. I don't know if it has anything to do with your extended warranty. No, I don't think that was the reason you got hacked. Okay. Because clearly, yeah, they want your email working so that they can send you those emails. So, but all right. Does anyone else have any other questions or comments about the whole situation?
So just to make sure, you said that everything was going to be pushed out a week, so meaning that it would be post spring break, like the exam.
Yeah.
Okay,
yeah.
perfect. Thank you, sir.
So, so with regard to this class, at least for now, I'll communicate through that email. Okay, that Gmail address. Okay. I guess I think it shouldn't be too bad for this class because I can now access Blackboard, so I can post stuff on Blackboard. I'm going to imagine everybody here can access Blackboard, right? If you can't, let me know, but I think so. And then obviously the other systems, Zoom and Gradescope, are totally unaffected. So instead of sending it out, yeah, we'll just communicate through the Gmail, okay? So, you can. Somebody can't. Yeah, okay. So Manny, have you tried to? Did you use the direct single sign-in link for Blackboard? There's two things. Okay, the page. No, but don't go through. So that's the thing. Okay. Maybe I can find it. If you go to, you have to go to, this is the other one that I think the university doesn't realize, that probably half of you don't have Facebook accounts, right? Because you're not 50 years old, right? I know my daughters absolutely do not have Facebook accounts. Like, I think one does, but anyway, I think it's on the Twitter. It's on the Instagram and the Twitter accounts as well. What's going on here? This is not working. But if you, I'm just trying to see if I can find the link. This is being weird. Well, okay, if you go to the university Facebook account or to the Instagram, the university Instagram account, and if you haven't done it, you probably should at least find those, because that's the only way the university is sending out information. There, is that it? Yeah, there it is, right. So there's a link that gets you into Blackboard without going to myutep.edu. Myutep.edu is down, so you can't do anything through there, right? They gave 2 links. One of them, you select third-party authorization, and there you type in your regular UTEP ID and password. For most people, that works. For myself, it did not work. So I don't know what happened. So the other one is also on the Facebook page. They posted a link. Obviously, the help desk is not taking any phone calls. So they set up a minors.utep.edu email for the help desk. And I'm going to forget what that is. But again, it's on the Facebook link. Okay. And you can email them. And for me, they were relatively responsive, and they had to it took like 10 emails, but they had to lock up my whole account. They had to install software on my computer or something. I don't know what they did, right? I'm being monitored, I think, even now as we speak, by the university. So I should be careful what I say. So, but they'll get you hooked up on that, okay, if you need to, all right? So you should be able to do that. Anybody else have any other issues? Yeah, well, you can, so again, your emails, your minors.utep.edu emails, they should work. But my email does not work, so you can reply to that email that I sent out today, which was like me-chair, well, I forget what it was, utep me-chair at gmail.edu, gmail.com, right? So that'll work, okay? Yeah. All right.
Real quick, for class on Thursday, is it just going to be regular class?
Yeah.
Okay. Thank you.
Yeah, we have to try to get back to normal, okay? But I mean, I don't, it's hard enough to communicate with students with this pandemic shutdown anyway, okay? So that was a challenge. Now, obviously, it's even more challenging because the department can't really get your information as well. So, but I believe I had Myra post that same email account that I used this morning to the department Instagram and Twitter stuff. So if you are having issues in any sense, you should feel free to use that email as well, okay? So since, as a department chair, you can contact me through that for issues that aren't directly class related as well, at least while this, we try to work this all out, okay? All right. Well, if that's fine, then maybe I guess we should try to get some work done. So I have to be honest with you, because I'm a little bit compromised here because this is being weird. I cannot use my keyboard. Let's do this by typing in manually. All right, well, let's move forward if I can. So what I wanted to cover today was statically indeterminate torsional problems. If It's letting me. My iPad is being really weird. You know, I'm gonna exit out and I'm gonna come back. Okay, don't go anywhere because there's something going on here. I've probably been hacked. Oh, I have two. All right. All right, I'm back. Yeah. I think to unlock my account, they like took over this computer, and I think that was the issue. So, okay. All right. So, let's get the share screen. So, you know, when we do the torsion problems, there's kind of a direct analog we've seen already through to the axial problems, right? So whether it is figuring out that the elongation for axial is PL over AE, or in the case of torsion, the angle of twist is, instead of the force, we have the torque, we have the length. Instead of the cross-sectional area, we have J, and instead of E, the elastic modulus for tensile Hooke's law, we use the shear modulus G. Similarly, we also could see that like we may have a statically indeterminate axial problem, like this, for example. Right, so this is statically indeterminate. And the reason it's statically indeterminate is because we have unknown reaction forces at the two ends. It's constrained at both ends. So we can only do, well, let's do this. Right, we can only do sum of forces PA plus PB equals PA plus PC. Right, and we supplement that with the equation that the elongation from point A relative to C is 0, right? And we use these two equations to solve this statically indeterminate for the axial problem. We have actually the same exact situation if we have a torsion problem. So in torsion, right, we can just replace the axial loads with torques. And so I know this is a bit cheating here, but that's if we just put like a double arrow on here. So the same exact analogous problem would be as follows. And I have stuff here. You know, if we look at it as a, you know, so if we had a system like this, which is fixed on one end. Let's call this point A. I'm going to call this point B. And it's also fixed here at point C. And there is a torque applied at B, right? We have reaction torques at A and C, all right? And if we do sum of moments around the axis of the shaft, right? We get that the torque at A plus the torque at C has to equal the known torque at B. But we have two unknowns in the same exact way as we had the two reaction unknowns for the axial problem, right? So we can only write one equation of equilibrium, but there's two things that we want to find. So we need to have an additional equation, right? So it's of course going to be supplemented by another compatibility equation, but obviously it's not going to be on the elongation. It has to be a compatibility condition on the angle of twist. All right. So here, the angle of twist of C relative to A has to equal 0. Okay. And so everything else really goes the same way. And let me just delete all this nonsense. All right. So again, if we look at something like this, just like when we had the compatibility condition for axial, we can write this as the angle of twist of B relative to A, the angle of twist of this section, plus the angle of twist of C relative to B, this section has to equal 0. And we can then use free body diagrams to get this in terms of, you know, the reaction forces. So for example, this term here, we can rewrite as the torque in section AB times the length of AB over J, but that's J for this section AB here as well, times G. Let's assume it's the same material for both, but if it's a different material, you know, you could have G for AB, right? And this term here is going to be the torque in shaft BC times its length over its J times G, and that all has to equal 0. So if we were to look at a free body diagram that cuts through AB, we would see something like this. So here is the unknown reaction torque at A, TA. Now, if we use the right-handed rule, again, to be consistent with the axial problems, here's the outward normal. So if we do the right-handed rule, I know I can't use my hand on the screen, but you know, that would mean that the internal torque, its positive sense, should be in this same direction. So this is the internal torque in AB. And if we do sum of moments around the x-axis, you know, if we call this the x-axis, then you can see that that internal torque TAB, this one here, has to equal negative TA, all right? And likewise, we can do the same cutting through section BC. And if we do that, draw a free body diagram for that one. So here is the unknown reaction torque at point C. And again, if we use a right-handed rule to expose the internal reaction torque, right, here's the outward normal going in that direction. And if we curl our right hand so the thumb points in that arrow, that gives us the positive sense for the internal torque in section BC. And now in this particular case, from this free body diagram, you can see that that does equal TC, right? So we can substitute those into here. And now we have minus TA LAB over JAB times G plus TCLBC over JBC times G all equals 0. So now we have a second equation that we can solve simultaneously with the equilibrium equation. And we have two equations that we can solve for the two unknowns, TA and TC. All right. Obviously, I'm going to do actual problems, right? But I want to do it like with letters now, just to show you that it's really the same approach. So everything we did before, we can do, for torsion, right? So we could have the problems where so obviously the one that I just did there was two elements in series, but you could also have a problem that looks like the following. Zoom in. There we go. You could have like a top plate with, I don't know how to draw this really well, but you can imagine inside here. So if we did a cross section, oops. We would have two different materials, right? Like this would be an inner material and then an outer material. So this would be two elements in parallel, right? So this would be like, let's say this is steel and this is brass, right? I don't know why, but let's say we did that. Then in this particular case, we apply a torque onto here, right? So that torque equals the torque from the steel plus the torque from the brass. Okay, that's our sum of moments around this. If you want to, we can call this the z-axis. And we don't know TS or TB. These are the torques, the interior reaction torques from the steel and the brass section, respectively. But we could augment this with a second equation, a compatibility equation, and it's going to be the same as when we had the axial elements in parallel, right? The angle of twist of the steel has to equal the angle of twist of the brass section, right? So that's the way it would work, okay? And I don't know, I'm trying to think. I honestly, off the top of my head, I'm sure there's some other cute ones that they do. I can't think of a gap one. There really isn't a gap one for torsion. So you would actually either have this situation or the previous situation. And you can solve this in the same exact way using either this direct approach with the two equations for the two unknowns, or you could also use a method of assumed forces, right? Where, for example, like on this one, or I guess we should say method of assumed torques, you could go to this problem here, remove one of the supports, right? And make, let's say, torque C have a value of 1 kilonewton meter, use superposition, and scale that torque at C so that, the total twist is 0, okay? So same stuff, all right? All right. So let's see if I can do a problem, okay? Let's find something. Well, I'm looking for a problem. This is always an area that I think has a bit of a discontinuity in the curriculum. How many people have been exposed to gears? Again, just comment. Like, I know, just turn off your mic and say it because I'm not looking at the screen. And if so, what classes have they talked about gears? Because I don't think you do it all, right?
I think so.
All right. Well, you may have noticed that there's some problems with gears in this chapter as well, with torsion, right? And they're not too bad, but they do give you a little bit of a. They had like a little bit of a twist, no pun intended, to these problems. Okay. I believe I posted a video where I don't think I do a very good job of it, but I do go over some of the basic equations for gears, but I will make sure to do one of those problems today as well, okay? That's fine. Yeah, that's easy. Okay, here's one. This is super easy, all right? All right, so this is problem 577. So this is pretty easy. This is very similar to what I just kind of quickly sketched out earlier, right? So we have a solid circular steel shaft, 40 millimeter OD. It's fixed at both A and B, and they give you a couple here at point C, all right? And they want us to figure out the maximum shear stress in AC and CB, and basically, where it is, right? Okay, so this is statically indeterminate, okay? And you can see that here. I should mention, it doesn't really show up in axial problems, but when we talk about something being in static equilibrium, that doesn't necessarily mean that the body is not moving. Static equilibrium means no acceleration. All right. So moving with constant velocity is still being in static equilibrium because the sum of forces is equal to 0, right? So we didn't really see it in axial problems, but in a lot of problems where we have power being transmitted through a shaft, whether it's by gears or belts or whatnot, we will very often have a situation like the following. Like this problem could be replaced by something that looks like the following. me just do this. So imagine that couple torque was provided by an intermediary gear that went off to another gear in a gear train. What is going on? Stop. And here they might give us a gear force of like say they give that and there's gears being offloaded onto this, right? So this whole thing is rotating with some speed, yes, okay, it's rotating. But that doesn't mean it's not in static equilibrium. So a problem like this is actually identical to this problem. So here they have points A and B fixed, but don't be confused when you see a problem that looks just like this, but the whole shaft is rotating with some constant speed. It's still a static equilibrium problem. This gear here is still exerting a reaction torque onto this gear, and this gear here is exerting a reaction torque onto this gear that are unknown, still have to be in equilibrium with the 300 kilonewton meter torque applied on the intermediary gear, and you know the total angle of twist still has to be 0. So the same stuff works, okay? But this one is like fixed, okay? All right. So I'm going to replace here, right? Reaction torque A, reaction torque at B, okay? And this couple produces a net torque of, it's 3 kilonewtons acting at a moment arm of 100 millimeters. So that is 0.3 kilonewton meters or 300 kilonewton meters, correct? So that's what's going on here. It's analogous to this one. All right, so we can call this the x-axis if you want. X, Y, and we can call that the z direction. So if we do sum of moments around the x-axis, that is going to give me the torque at A plus 300 kilonewton meters plus the torque at B equals 0. All those torques, the way I drew them, were right-handed sense, so obviously probably the torque in A and B are going to be going the other direction, but that's fine. I'm just going to leave it that way for now, okay? All right. Don't know this, and I don't know that, right? So, okay. So how do we get a second equation? Well, we're going to use the fact that there's no rotation between ends A and B. So the angle of twist of B relative to A, which equals the angle of twist of B relative to C, plus the angle of twist of C relative to A, that has to equal 0. And this is going to give us the second equation, right? And so this is all going to go the same way. So if I were to, again, put a cut through section AB, just like I just drew before, we could see that the internal reaction, well, I should just draw this. Shouldn't go too far. All right, so here is torque at A, and then if we do a right-handed torque here, this is the internal reaction torque in shaft AC, and that has to equal negative A, okay? And likewise, we can do the same here. Let's do it this way. So here is the internal reaction torque in shaft BC. And here is my support reaction torque B. All right. So in this particular case, this is actually equal to torque B. All right. So now I can rewrite each one of these terms. So the angle of twist of section BC, this section here, is the torque in that section, which is that torque. This is torque BC, but we know that is going to equal the unknown reaction torque at B times its length. The length, well, I wrote over this, right? What is that? It's 600 millimeters. So the length is 0.6 meters. We're going to divide that by J, but J is the same for both, and G is the same for both. So I'm just going to leave them there like that for now, and you'll see why in a second. Now we have the angle of twist in section CA, so that one. So that is going to equal the internal torque in AC times its length, which is 0.4 meters. This internal torque here from this free body diagram equals negative TA. And this is also over J times G. And all that equals 0. So you can see here why I didn't really have to calculate J or G, because I can just multiply this equation by J times G, and I'm just going to get 0.6 TB minus 0.4 TA equals 0. Or in other words, 0.6 TB equals 0.4 TA, right? All right. So that's our compatibility condition, kind of tweaked a little bit or simplified. And we still have the equilibrium condition, TA plus TB equals negative 300 Newton meters, right? Okay, whoops. So this is relatively easy to solve, right? We can use this equation here, the first equation, the compatibility equation, and easily substitute that into the equation below. So I don't know, let's get rid of TB. So, well, okay, we can get rid of TA. So TA, this one can give me that. TA is equal to 6 over 4 TB, which is going to be 3 over 2 TB, right? And if I take that and I put that into this equation, that's going to give me the following. 3 halves TB plus TB equals minus 300 Newton meters. And obviously, this is a 2 halves, so this is 5 halves TB equals minus 300 Newton meters. And we can solve that. And we're going to get yeah, I could fix easy. Right. All right. So we know TB, and then we also can use that to get TA in here. So that means that TA is going to equal minus 3 halves of that, or 180 Newton meters. So if we were to redraw this system, it would look like the following. All right, in the middle at point C, right, we have the 300 Newton meters here. At point A, we have the reaction torque. It's going in the opposite direction, right? It's a negative, so it's in the opposite sign of the way we drew it. Let me zoom out so you can see that. Right, I originally drew it up here in the right-handed direction around the x-axis, but it's a negative, so it goes the other direction, and that's point A. So this is 180 Newton meters. And likewise, at B, it also goes in the opposite direction, and it's 120 Newton meters. Okay? So thankfully, 120 and 180 add up together to give you 300, right? So now we know the reaction forces on this shaft. Okay? The problem wanted us to know what is the max shear stress, right? What is the max shear stress in a C or a B? Okay. All right. So here we're going to use, now that we have the forces, we're going to use the torsion equation, tau equals TC on J. I guess now I will have to calculate J, but that's fine. So which one is going to be have the greater stress? Section AB, I'm sorry, AC or CB? Is it going to be here?
BC.
BC?
Yeah.
How do you know?
Well, because if we cut section AC in half and solve for the internal shear stress, then it would be opposite to 180
Right.
Newton meters. And if we do the same to the other side, to BC, it would be 120 Newton meters, and 180 is higher than 120.
Oh, okay. So you said, oh, I'm sorry. I thought you said CB, right? So you said AC, right?
Yeah,
Yeah,
AC.
right. That's right. Right. Exactly right. It's going to be AC. But again, I do want to state, and you said it perfectly. So good job on that. You said draw the free body diagram that, where it shows the reaction force in there, right? It's not that this is 180 and this is 120, but the internal reaction force in here is 180. And in this particular case, the internal reaction force in here is 120. 180 is greater, so that's going to be the limiting case. Yeah, perfect. All right. So it's going to be in AC, and that's because in section AC, the internal torque is the 180 Newton meters. Okay. And actually, technically, to be correct, it should be the negative, right? No, actually, that was positive because it's negative. Yeah. All right. What's going on here? Why is this doing okay. C is the radius, and it said 40 millimeters, so that is 20 millimeters or 0.02 meters, and J is pi over 32, that diameter, 0.04 meters to the fourth power, which equals a very small number. Yeah. 0.251 to the -6 meters to the fourth power. Okay. So now we can plug all that stuff into here, and that's going to give us tau equals 180 Newton meters times 0.02 meters over the 0.251. And that's going to give us a number. So that gives me 14.3 megapascals. That's the answer. That's the shear stress. Okay. All right. So very similar to the axial ones. Okay. Any questions about that one? Let's see if I can find a more interesting problem. See if I can find a gear one. I know I got gear one there. Right. Not just of a gear, but a gear one. All right. So this is a tough one. Okay. So yeah. Okay, so here we have two shafts that are connected by the spur gear pair shown here, okay? And now again, it says the shafts are fixed at their other ends, A and B, but honestly, more typically, it's not that those are gonna be fixed, but those are gonna be connected to other gears or pulleys or some clutch or something that's driving a component, and there's probably power being transmitted down these two shafts, right? But again, a static problem is constant velocity as well as no velocity. Okay, all right. So obviously here we have unknown reaction forces at A and B. Let's kind of set up a little bit of a coordinate system to make my life a bit easier. So I'm going to call this, again, let's call this the x-axis. I'm going to call this y and z, although we really don't need y and z, but might as well just close it out. All right, and if we do this all in the positive sense, let's just draw the unknown reaction torque at A around the positive x-axis. Are we good? Okay, we'll do the same at B. So those are my unknown torques, right? And clearly we have a statically indeterminate problem here, right? Okay, so I can write equilibrium for the whole system. TA plus TB plus 500 Newton meters equals 0. So that's just sum of moments around the x-axis, if you will, for the whole system, right? But obviously, I got two equations for two unknowns. So this is statically indeterminate. I need a compatibility condition. So how do we do this? What is my compatibility condition I'm going to use here? What's the kinematic condition we can do? Like I need another equation, right? Are y'all asleep?
Could it be that the strain of AE equals the strain of FB?
No, not the strain, right? So remember, we're usually always going to. Oh, maybe there's a way you could do it with strain, but not only that, it's usually in terms of the motion, but actually the strains don't have to be equal, right? Strains and stresses don't have to be equal. Forces, that balance each other out, right? Any other ideas? Well, if somebody wants to, they can use the really the cop out one at the top level. Can you think about like an angle of twist condition for the entire system? Just like I wrote this, even though there's multiple components in here, I still can write, equations of static equilibrium for the entire system. How about this? Is that true? What's the angle of twist of face A relative to face B? It's got to be 0, right? So that's the easy part. The hard part is now, right? What do we do when we have to break this up? So normally I would say angle of twist of A relative to E plus the angle of twist of, well, is it E or let's do this one, F relative to B equals 0. So this is actually not correct. Why is this problematic? What is the issue we got going on here? You can even just tell me physically what it is. It's those things in yellow, right?
The gear. or
Yeah, it's the
different
gears,
radius.
right? So if let's look at this angle of rotation, right? If E, let's just say, for example, let's say this gear here, gear E, let's just say it rotates 360 degrees. Now, again, this is looking down the x-axis, 360 degrees in a clockwise manner. How much does gear F rotate? See, before, when it was one continuous shaft, it was easy, right? Because before, what we would have had was A, B, and then all this nonsense here with the two gears would have just been like point C, and they would have just given you the one torque here of the 500 Newton meters, right? But we don't have that now. It's a little more complicated because of those gears. If gear E rotates one full rotation, how will gear F rotate?
Does it do 2 rotations?
That's right. Okay, right. Now, why do you say 2?
Because it's half of its radius.
Right. You're saying, okay, it has to do with the fact that the gears are in contact and you have this gear reduction ratio, which is related somehow to the diameters of the gears, correct?
Yes,
All right, that's true. How come you said a half and not twice?
because, oh, did I say it would rotate twice as much, or?
I forgot
Half.
what you said. Did you say half or twice? Did you say? I think you said twice. Okay, how come you didn't say half?
I was gonna say half at first, but since the road, I just like imagined it kinda.
Mhm.
Since like this one's bigger, it rotates one time, and this one doesn't have to rotate as much pretty
Yeah.
much. I don't know how to
That's
explain it.
That is perfect. That's exactly right. But the way we can do it, we can say it a little more mathematically, is if we draw the two gears, right? Okay,
So you would have a bigger circumference in gear F in that case.
exactly. What happens is as the two gears rotate, let's say let's say here's a reference point on gear E, and I'm just going to rotate it a little differential amount, right? Let's call this D phi E, right? So the arc length that it sketches out is here. That has to be the same arc length. The two gears roll in contact. There's no slip. So these two arc lengths have to be the same. So this angle here is something different, D phi F, but these two arc lengths here, I know I drew this really small, so I apologize for that. But this arc length has to equal this arc length, right? So this arc length here is D phi E times the radius of gear E, right? And that arc length has to equal this arc length, which is going to be the radius of gear F, D phi F. Those have to be equal. So that tells you that the ratio of D phi F equals the radius of, E over the radius of F times how much gear E rotates, okay? And not only that, actually, they rotate in the opposite direction, so we get a minus sign there, all right? And it kind of makes sense, right? They have to have the same circumference, right? So you do one full rotation, right? The circumference of gear E is bigger than the circumference of gear F. So gear F has to rotate more times than gear E. Does that make sense? You know it's always going to be associated with the ratio of the two gears. And in this case, since one gear is twice the other, it's either going to be 2 to 1 or half 1/2, right? 1/2 or 2/1. And the way I always remember is like, I try to visualize it just like I think it was Max said, the bigger gear, since it has a bigger circumference and it has to match the circumference on gear F, it's in the time it takes to do one rotation, gear F is going to have to do more rotations. So it's going to be twice as much. But this is the way it's sort of shown mathematically. And if you look at this, you can see obviously here, the radius of gear E is twice the radius of gear F. So this gives you that. The angle at twist of F is -2 times, not the angle at twist, but how much gear E rotates, okay? So it's always going to be by, first of all, you always know if one gear is going clockwise, the other one's going counterclockwise, right? And the ratio has to do with the ratio of the gears, right? And I always get confused as to whether it's like twice or a half, assuming the gear ratio is 2 to 1 or whatever the gear ratio is. And the way I remember is I exactly do what you were saying. I try to kind of visualize it in my head, and I realize that, the smaller gear goes faster than the bigger gear, right? And so that's going to give me a check as whether it's 2 to 1. Or if you're really quite adept with the abstraction of math, you can just do this, but I usually do that better. So, okay, so that means that if it rotates 360 degrees, gear F is going to rotate twice as much as that. So that's 720 degrees, and it's going to rotate in the other direction, okay? Or in other words, the angle rotation of gear E is always going to be equal to, does that make sense? So now I used exactly what you kind of said as far as like the physical intuition of how this happens, and I've written it mathematically. So now, okay. So now I've really made this really complicated. So how do I move forward from here? All right. So let's take a step back, right? We wanted to somehow deal with this condition that the total rotation from A to B is 0, okay? But this equation that I wrote here really does not work because, you know, if you look at this, basically what we're saying is whatever shaft the first shaft rotates, the other one has to rotate by the same amount, but in the opposite direction. But that doesn't make sense because there's this gear reduction ratio. So how can we kind of how do we take account of this? What can we do?
Would it be the same equation with just kind of including the 2 on the angle of E?
Yeah, this one's actually not too bad, right? Now, remember when I wrote these fees, right? These fees are actually like the rotation of gear E and the rotation of gear F, right? But let's be a little more careful, right? So let's do it a bit more formally, right? So we want a relationship of shaft A relative to E and something involving the rotation of shaft F relative to B, right? So, you know, so let's look at this for the first shaft, right? So A is fixed, right? So the rotation, how can we relate the rotation of A relative to E? I should use a different color here. Oops, where'd it go? Okay. I'll use this crazy color. Right, we want the rotation of face A relative to gear E. How is this related through to this? So again, you can kind of do this physically. Use your, I don't know if you can still see my camera, right? If you look at my camera, right? Imagine this here is A and this is E, right? So A is fixed. If gear E rotates in the way we're showing it, it's going this way, right? We're calling that a positive rotation, right? So if we talk about relative motion, isn't that the same as face A rotating this way relative to E? You see how it's going in the other direction, right? So that's actually, it's a negative, it's of opposite sign, right? So the rotation of A relative to E in this particular case is equal to the negative, the rotation of E, right? I don't know if that makes, that's a little harder one to see, okay? Likewise, if this is FB, this is FB, here is F rotating in the positive sense, right? Well, that is F relative to B. So actually, in this particular case, the angle of twist of F relative to B equals phi E F, right? So if I use this, all it's actually what it's done is just change the sign. So if I use those conditions into there, I'm going to get the following, right? That 2 phi A E equals phi F. Oops, I'm sorry. All right, does that make, now the reason why it flipped sign is because of the fact that we're looking at, it's really because of this one. This is the one that's causing the issue, right? This phi E, right? This term here is actually the rotation of gear E, like relative to the fixed space. The rotation of face A relative to E is kind of the opposite of that because A is fixed and E rotates. So A rotating relative to E is actually the same as E rotating in the other direction. So that's why we get the sign change. So now this here actually is our second equation. So we're going to use this equation along with this equation here. Those are our two equations we're going to use to solve the problem. There's other ways to think of it, right? But that's how we do it. Is there any questions on that while I try to get my screen unlocked? There we go. Okay, so now for this one, what we can do here, right? This is going to be just simply the torque in AE times the length of AE over, and I think they're the same shaft, so it's J and G, and that equals the torque in FB, length of FB over JG. We can multiply JG, they cancel out, right? The length of AE is, I should just look at that, is 1.5 meters, and the other one is 0.75. Oops, sorry. So I got in front of my two. So 2 times the internal torque at AE times 1.5 meters has to equal the torque in FB times 0.75 meters. And now we want to use the sort of the free body diagrams to get these in terms of the reaction torques. So let's look at that real quickly. I know it's the end of class, but okay. So if we go back to here, if we draw a free body diagram, excuse me for doing what I always complain about, making sloppy free body diagrams. Here is torque A, and then this would be the torque, the internal torque in AE, right? And so that's going to equal torque A, just using the right-handed sense on everything. And if we do it for here, we're going to get torque B going that way. And again, if we use a right-handed rule, this is the internal torque in BF, which equals minus the reaction torque at B. So now I can substitute those into here. And now, so I get, well, 2 times 1.5 is 3 times the reaction torque at A equals 0.75 minus the reaction torque at B. Okay? And so there you go. You can solve that out. All right? That's the end of class, but anyway. Okay, any questions on that? That one's a little tricky. I think if you just physically think about it, how it rotates, right? But also try to back that up with writing the mathematical equations. They're not super complicated equations. It's not like Schrodinger's equation. I think it'll help you kind of get some confidence in, again, solving these problems where, you have to use your spatial abilities to kind of get through the complexity of the problem. This problem is not any more difficult than the problems without the gears, right? From a sense of mechanics and materials, but obviously trying to do the spatial, like, bookkeeping of what happens because of the gears is what makes it complicated, right? This happens a lot in engineering problems, but I still always maintain, if you go slow, try to physically think it out, but also try to express what your physical intuition is mathematically, That's the thing that allows the problem to kind of fall apart. Okay. All right. Let's stop there. All right. Like I said, I'll send out updates on what's happening, what homework. I'll update the homework assignments and all that sort of stuff as well on Pearson. Okay. All right. Very good.